Let's begin lesson 3. Intercepts is the first topic, X and Y intercepts, and it says to you that they're points where the graph crosses or touches the x-axis or the y-axis, and for each one of them, one of the coordinates will be 0. So if I have this equation right here, and I'm going to say that I'm going to start with y equaling 0, that would mean that I'm finding the x-intercept. And so I say that I have 0 squared minus 3 equals x, and boom, now I know that x equals negative 3 is where that intercept lives. So it would be, negative 3 and 0. If I set x equal to 0, then I am finding the y-intercept, and I can say that y squared minus 3 equals 0, and I'm going to add 3 to both sides. Y squared equals 3. Take the square root, and I see that y equals positive and negative square root of 3, which means that there are two y-intercepts. There's a y-intercept at 0 and positive square root of 3, and at 0 and negative square root of 3. So he doesn't ask you to graph, but one of the things that's coming up is called curve sketching, where we try to sketch something by knowing about particular points. Like if I can find a maximum, then I could sketch that maximum. If I know where there's an intercept, then I can sketch that intercept. And then I'm going to try and put it all together. So this first one at negative 3, that I believe is going to be my vertex. Vertex of what, you say? Well, I know that y was squared. I don't know why that line looks so weird. Y is squared, and x is not. If x was squared, I would know for sure that it was a parabola. But since it's y that's squared, I'm guessing, I believe, that this is a radical function, right? Where the parabola has been turned on its side. And that's why I have a positive square root of 3 as an intercept and a negative square root of 3. By the way, the square root of 3 is like 1.707. I just happen to have it memorized. You probably don't. One good one to keep memorized is the square root of 2 because it comes up in trigonometry. That's 1.414. So if you don't have it memorized, you could still guess, right? The square root of 4 is 2. So the square root of 3 is got to be just a little bit shy of 2. So now that I have graphed those little pieces, I will say, boom, that is what my function looks like. When we look at symmetry, it's important for us to be able to say whether or not we think a shape has any symmetry, and if it does have symmetry, on what axis does it have symmetry. We have y-axis symmetry, and we have x-axis symmetry, and then we have the symmetry that y equals x. And these are three examples of those kinds of symmetry. Okay, and so this one is like a rotational symmetry, that if you rotate this and you keep rotating it, that it will turn into itself. Okay, this one is like if you folded the piece of paper in half, and this one again is like if you folded the piece of paper in half. And so graphs can be symmetric, but they aren't always. It turns out that there are tests for symmetry, formal tests, which I will show you, and informal tests. The informal tests are a little bit easier to use and a little bit more intuitive, but they are not foolproof. So you need to think about whether other numbers would work the same. And if your substitution produces a 0, then perhaps you need to find another number, because sometimes if you were checking at the vertex, you won't be able to tell whether or not you hit. This is where I got to learn how to use a transition. Yay! So I wanted to show you what the graphs of these things look like, and I don't want to have to write while we're talking about it, okay? So I've already pre-printed I've already put the graphs into Desmos, and I've already got the answer key to the lecture notes open. And I want to show you about these tests. The informal test says plug in any number and see what you get. Now, this equation right here is the number that we're plugging into. And he's not showing his work, so I just wanted to tell you 2 with 1 in parentheses with a cubed on the outside minus a 1. You work that out, okay? And Desmos will work that out for you. Ready? F of 1 is what? It's 1. Well, what is f of negative 1? Shoot, that is negative 1. Yay! That means that we can look at this and say, ready? The informal test says that if we, ready, substitute a number and its opposite for x, it will give us the same y value. That would have been y-axis symmetry. That's not this. X-axis symmetry, substituting a number and its opposite for y gives the same x value. That's not this. No, we are right here, which is origin symmetry. And look at the graph. You can tell that it's origin symmetry. It is symmetric to this line. If I rotate this shape around, it turns into the other shape. So let me say this again. Substituting a number and its opposite gives me opposite y values. That's the informal test. The formal test says take x and negative x and y with negative y, you will get an equivalent equation. And that will tell you that you have origin symmetry. So he shows that work, okay? That he plugged in what happens when you throw a negative x in and that you throw a negative x in. And when you work it out, you get this, which is exactly the opposite of the original, okay? And that's how you know you have origin symmetry. Now, I don't necessarily need you to be able to do this except for one problem on the AP exam. And I guarantee you, you can pass the AP exam without being able to do this. But talking about how graphs are shaped and giving you chances to see, hey, a cubic that has a little minimum, right? This would be, I would call this a local minimum and a local maximum. Being able to recognize and see the zeros of a function, that's the real teaching goal here. So when you see like my objective, you say, oh, it's to learn how to be able to decide whether or not I have an even or an odd or an origin symmetric function. Yeah, no, that's not actually my teaching goal. My teaching goal is just to teach you Desmos and to have you be familiar with these graphs, okay? So number 3 is the next graph, and I'm going to turn this one off. It says that if you plug in 1, that you get a negative 1. And if you plug in a negative 1, you also get a negative 1. So I will do that on Desmos. See, there's G. And here's G. And ta-da, I'm saying that both of those have a value of negative 1. So if I plug in a number and its opposite, I get the same output. So let's look at those lecture notes again. We're zooming back over here. We say then that we substitute a number and its opposite, and then we get the same y value. Boom, means that it is symmetric on the y-axis. I fold this paper in half on this line, and those two lines will meet. The work goes like this. If I plug in everywhere that there's a negative x, if I plug in that everywhere that there is an x, if I plug in a negative x, well, what happens? Well, it doesn't matter. If you absolute value something that was negative, then you're going to get a positive. So you could have started with the positive. So this is exactly equal to that. They're the same thing. And so that's your formal test. So by informally looking, we can check and see that we say it has y-axis symmetry, and also by looking at plugging in the negative x value, if we get the same equation twice, then we can say that it has y-axis symmetry. All right, for number 4, here you go. And I'm going to get rid of that one, and I'm going to throw that one in there. This one is a little bit more tricky. I would say it's not graphing. Oh, there it is. There it is. Okay, it has an X Intercept at 2. That makes sense to me now that I think about it. Okay, so that guy is not a function. We could tell it's failing the vertical line test. If I put a line through this right here, it touches twice. The other thing is I plug in a number and I get two values out of it. So because I get those positive and that negative, that gives me an indication that it's not one to one, right? One input should give you one output. That's a line. Okay. If you use a parabola, it is a function. You have two different inputs, could get you one output. That's still a function. This is not a function. The other thing he wants you to note is that opposite y values produce the same x value. So at any time I plug in any y, I could have plugged in the positive or the negative, and that's going to cause me some trouble. So it is not a function, but it is x-axis symmetry, okay, because I can fold it right here on this line, and then that gets me in the same shape laid on top of one another. And for that, remember, our tests, the test that we are using was that if we put in a number and its opposite and we got the same x value, that's what happened. And we replace y with negative y and we got the same answer, the same equation, then that means that it is x-axis symmetry. Okay? Here, and I just want to talk about even and odd because those words accidentally popped out of my mouth with the last example. It says it's even if f of negative x and f of x are for all x in the domain. So we were saying that if we could find y-axis symmetry, then that's because if I plug in a negative x, I still get the same equation. That informal test that gives you y-axis symmetry, well, we are now giving you a definition for that. We call that even, okay? And what you'll notice is that something is going on with all of these equations exponents. Even. Let me draw a picture of it one more time. Parabolas are even. They have y-axis symmetry. There's a happy parabola. There's a sad parabola. As long as it has not been shifted, as long as the vertex is on the y-axis, as long as it hasn't been shifted left, it has not been shifted right, then it has y-axis symmetry. That is called an even function. And you may notice all of those exponents are even. As long as the exponents are even, you can add or subtract any exponent as long as it is even. Okay, and you will get an even function. Now, the only thing about that, though, is that this does not work, right? Y equals x squared plus 4x plus 3. That is not even. It is a parabola, and it has been shifted. This parabola has been shifted off of the x-axis, off of the y-axis. And you can tell because that guy has a hidden invisible 1, which is odd. So this is not even. It is also not odd. Okay, so now we have the definition that a function is odd if you throw in the negative x into your function and then you check to see what happens if you absolutely negate your f of x, then boom, that would mean that it is odd. And here I'll say that exponent is odd, that exponent is odd, that exponent is odd, and all of these exponents are odd. So again, you could add or subtract any odd exponent and you would still have an odd function unless it has been shifted off of the origin. Okay, because remember, origin means that it is symmetric in like a rotational way. So I will draw a picture of such a thing and it might look like this. You see? That is rotationally the same. Meaning if you pick this quadrant up and you flip it, it will end up into that quadrant. Or if you pick this quadrant up and you flip it, it will turn into that quadrant. As long as you keep rotating, it will get there. So we look at this equation and we say it is also not odd. And the reason it is not odd is because that equation, like I said, it got shifted. I want to say that it gets shifted like this, so the vertex is off. So if the vertex is over here, that doesn't work. All bets are off, okay? So those are your examples. Those are your definitions of odd and even. And now I would say we should put these in and check to see what we get. Put them into Desmos. You'll see that there's a 3 here and a 1 here, and you could tell me, yes, you know for sure that it is odd. However, having said all of this, some of you are very particular. You actually want to do the work and you don't want to just cheat and have some sort of trick memorized. Some of you maybe are worried that if you could keep the trick memorized. I don't blame you because I have difficulty. So let's actually do a problem. I want to figure out what f of negative x is. And f of negative x is negative x being cubed minus a negative x. And when I work that out, what I end up with is a negative x cubed plus x, which is exactly the opposite of my function. Let me double check the opposite of my function. If I take my function and I apply a negative to it, so I had x cubed minus x. If I apply a negative to it, then what do I get? Ready? I get negative x cubed plus, because a negative times a negative is a positive, plus x, which is, check, the same thing. Therefore, I know this is odd by the formal definition. Now for g of x, I am guessing that it is even, okay? And when I do check to see if it's even, I'm guessing that it is because I think it's a parabola. I know that it lives with its vertex at the origin. It's at on the y-axis at 0, -4. And so why don't I just try this test, okay? Can I plug in g of negative x where I turn that x negative? Yes, that works. Look, negative x times negative x is a positive x squared minus 4. This matches that, and therefore this is even. Okay, the last one. I already told you the answer, so you could tell me you're pretty sure the answer is neither, because this is even and this is odd. Yes, I agree. Okay, but let's actually try it. If we think that it is even, we still want to know what happens when I plug in that negative x. So h of negative x means that I say that I have negative x being squared plus 2 times negative x and plus a 2. And then I could simplify that to x squared minus 2x plus 2. It does not match. It does not match that. It's different. Also, I want to know what happens if I just negate my whole function. So the whole function was x squared plus 2x plus 2, and I want to negate it. That turns negative, that turns negative, that turns negative. Negative x squared minus 2x minus 2, and that is not the same equation. So the answer for this one is neither. All right? Now, when we get to the very bottom here, we are being asked to solve one equation for one variable and to substitute it into the other equation. We solve both equations for the same variable and set it equal if we want to do method 2. So it says, without a calculator, find all points of intersection for those graphs. And I want to mention, you could plug those graphs into Desmos and you could find out where they intersect. This is supposed to be a moment where we are being true to algebra, where we're using algebra to prove what it is that we see when we graph. So the first thing I'll say is that neither one of these is solved for a variable, so I might want to solve for y. So I'm going to minus 1 from both sides, and I'm going to add y to both sides. And I'm going to say now that I have y equals x minus 1. You see, these were opposites, those were opposites. I'm bringing the y down, I'm bringing the x down, I'm bringing the negative 1 down. Here, I'm going to add y to both sides, and I'm going to minus 3 from both sides, and I'm going to say this disappears and that disappears. I have y equals, ready, x squared minus 3. So if I am doing method 2, I guess that's what I'm doing here is method 2, I have solved both for the same variable, and now watch me go. I can say x squared minus 3 equals x minus 1, and I'm going to minus x from both sides, and I'm going to add 3 to both sides, and I am going to get, oh, why did I do that? Hold on. I just want to put everything on one side. Okay. Aha, I guess I am doing method 2. I realize that now. X squared minus 3 equals x minus 1. I'm going to solve this by getting everything over to this side. Opposites now equal 0. I have x squared minus x minus 2, and I know how to factor that. I totally remember factoring. That this is an x minus a 2 and an x plus a 1, and that equals 0. So my answer is that x equals 2 and x equals negative 1. The method 1, I wasn't thinking about it. It says solve one equation for a variable, not both of them, and substitute it into your equation. So we could think about it like this, that I didn't need to do any of this work, because I can solve one of them for y, and that one, the first equation, was easiest. So x squared minus, ready, y is that whole other function. It's this piece right here, x minus 1. So distribute x squared minus x minus 1 equals 3. Sorry, plus 1 minus 3 minus 3. I end up with an x squared minus x minus 2 equals 0. And I factor it the same way. X equals 2 and negative 1. And boom. Algebraically, you can see both of them work out. And setting two things equal to each other is an essential skill in calculus. And it is actually a requirement that you be able to do this at some point in the free response section of the test, just so you know.